For the next session, we're going to dive now into cryptocurrencies, which I know if you're anything like me is a topic that probably fills you with a great deal of interest. I first heard about these a few years ago now and really didn't have the right mental model at all as to what they were and why they were working and what was interesting about them. Our first speaker is Aviv Zohar. He is a senior lecturer at the Hebrew University in the School of Computer Science and Engineering. The first comment I will make about Aviv is that his PhD advisor is a Harvard alumnus. Indeed, so Jeffrey Rosenshine, who I mentioned in my opening remarks, was Aviv's advisor at the Hebrew U. Aviv's an expert, I would say, in the intersection between AI and systems and economics. He's a very broad thinker, and he's a rapidly rising star. And he has been my go-to person to understand cryptocurrencies. And so with that said, I think we're very, very lucky to have him here to explain the mysteries. And please join me in welcoming him.
Thank you for having me. It's such a great introduction. What I want to try to talk to you about today is a very hot topic. It's Bitcoin, but I really want to try to get at it from a slightly more technical angle. I know the room is people with different backgrounds. Some probably know how Bitcoin works and how the blockchain works. I'll still get to try to explain it to others who don't. So what I'm going to try and convince you of today is that cryptocurrencies like Bitcoin are not just this fad that we hear about in the press. They're actually a technological tour de force. They are an application area for innovation in computer science that spans many of the subfields, of course, incorporating ideas from economics, game theory, and other relevant areas. And that innovation, things that we thought were impossible to do in computer science just a few years ago, are making their way into cryptocurrencies. So I want to start very simple. Before we had digital money, maybe the most simple form of transacting was with physical goods, right? With cash, with physical tokens. So this is an Israeli 1 shekel coin, if you don't recognize it. But when you transact with someone, he gives you a service or some item, and you simply hand them the coin, right? So matter has this nice property, the conservation of matter. When you give it to somebody else, he has one more, you have one less. And that is a fundamental property of money. At some point, we bumped into the internet, right? The internet happened to us, and we figured out that we want to send things quickly. We can send information very fast around. The problem with information is that it doesn't make for a good token in the same sense as matter does. If you transmit information to somebody else, they have the information, but you can also keep a copy. It's very cheap to duplicate information, so we cannot use information in a direct form as a form of currency, right? You cannot just give somebody bits, and then he'll give it to somebody else, and you'll have less, but rather information is easily duplicated. So when people started thinking about digital forms of money, what happened is that they actually switched to a new way of transferring money. And this is depicted in this very simple cartoon. You can think of some computer, maybe at your bank or somewhere else, holding in its memory the account balances of people. And when you want to send money to somebody, for example, if the blue agent wants to send money to this red guy, he just simply notifies the bank and says, please change the account balances. And the bank would make the change. So there are no physical tokens moving around anymore. There's just a representation of them in memory. So that is maybe in a caricature form the evolution of digital cash. And now what you have to notice is that we inserted somebody into every transaction that wasn't there before. Whereas before we could transfer coins from one to another without anybody intervening. Now we have to get the bank's permission. The bank might charge fees. There might be expenses involved. Our privacy might be violated because the bank now knows who we're transacting with. And the bank can also decide to take our money away by changing balances arbitrarily, maybe. We have to regulate it. We have to control it. It's another form of risk. So Bitcoin and other cryptocurrencies came along and decided to try to mitigate that risk and to increase the competition in the system in the sense of who can transfer your money by breaking up this entity, the bank, into much smaller pieces, basically a lot of computers that will be networked together in a peer-to-peer system. And these will function as the bank did before by keeping your account balances. So the approach that Bitcoin and other cryptocurrencies take is very brute force. They simply replicate the same information everywhere in all of the computers on the Bitcoin network. So now the system, which maybe took a very costly design choice, has to justify this somehow, right? So these guys are basically going to check each other's work to make sure that when money is being moved, it was actually you who requested it. No money can be seized or frozen, and there is competition on the fees that you're going to pay. Each one of these nodes can actually approve your transaction. So the fundamental problem, however, that arises when you start to replicate information like this is very foundational in computer science, and this is that you have to have everybody agree about what the information is. If there are different versions at different nodes, then we haven't done anything. There's no agreement about where money is. And in fact, this problem of reaching consensus on information is one that was solved in computer science. The difference is that when cryptocurrencies showed up, they wanted to do this a little bit differently. They wanted to have an open system where everybody can join, right, in some sort of a permissionless manner. You could become a node in this network without having to inform anybody, without having to request anybody's permission. And this was something that was unknown. We did not know how to synchronize information in such systems. And the reason this is hard, and the original problem is difficult, is that someone might try to confuse the system, right? If you were malicious, for example, if I'm this blue agent, I can decide to send messages moving my money to two different locations. Maybe one message sending all my money to the red guy, one message sending all my money to the green guy. And both of them are, each one separately is a legitimate message. If you read it, I'm just requesting transfer of my funds. The thing that the blue agent might try to do is send these messages to different computers in the network. So if they would now update their account balances, we would have discrepancies. We need to agree about which of these two occurs and which one doesn't. And this is a deceptively difficult question. It sounds very simple. What's the problem? Let's just communicate and choose one. But it turns out that this is hard, and especially what makes it hard is that the attacker here can have control of some of the computers on the network. Right? This is, again, an open permissionless system, so we might find ourselves listening to messages by some of the computers claiming different things that might try to confuse us. Now, you probably heard of the blockchain. This is how Bitcoin eventually solved this problem. And when I say Bitcoin, the solution appeared by an anonymous person called Satoshi Nakamoto. We don't know who Satoshi is, in spite of all the claims that you've heard in the media. And the blockchain is really just a data structure that holds all of the information inside of Bitcoin, right? And it's made out of individual blocks. Each one of these blocks is just a collection of transactions that one of these computers on the network processed and thought are okay and could make their way into this ledger that contains all of Bitcoin's transactions. So one way to think about this blockchain, these blocks are actually chained together with references, each one pointing to a predecessor upon which it builds. And you should think about them as a history of all of the transactions that have transpired in Bitcoin from the start. So if you read this, and the first block was published early in 2009, you read through, you can actually follow all of the money by following all of the transactions that were accepted, and you reach the current state of affairs. You know where the money is today if you just read through the whole thing. So this is just the log. And as new transactions happen on the network, this log gets extended. So one of the computers on the network might try to build a new one and include these transactions that were requested from it. And of course, to keep things consistent, when a computer sees one of these requests to move money, red wants to move all of his money to blue, and then a conflicting one comes up, red wants to move all of his money to green, we're not going to allow that in. That history has to be somehow consistent. The problem is that because different nodes have different points of view of what transaction showed up first, we might have another computer on the same network trying to create the same block that would extend this chain, and he might have seen that transaction first, right? So essentially, these conflicts in transactions appear in Bitcoin as these forks in the blockchain that represent alternative histories of what are the events that have occurred since the beginning of the system, right? So you can think of them, right? Each one is a version of events that you might support or believe is the one that actually had taken place. So Bitcoin has to somehow choose between these different events. If somebody shows us two versions of history, we need to choose one for everyone to agree on. And this is done using basically 3 rules for the currency. The first rule is that every computer, when it's presented with several alternatives, is supposed to pick the longest chain. Okay? If you see several chains and one is longer than another, right, a fork here ends up in a shorter chain, you're supposed to pick the long one. And the intuition that you want to have about this is that essentially extending a chain is like a vote of confidence in this specific version of events. You're saying this is the one that I think should take place. And the second intuition that I want you to kind of have when you think of the longest chain is that this induces a winner-takes-all dynamic. When a node extends the longest chain, it becomes even longer, which makes other nodes extend it as well, which eventually will mean that this fork in the chain that was shorter than others will die out. Nobody will build blocks on top of that. And then we have a very clear winner about the history of transactions. That's whatever is on the longest chain here. So that's basically how Bitcoin comes to agreement about the history of transactions. The second rule, which is rather obvious, is to quickly send blocks to all other nodes. When you receive information about one of these blocks, you send it out to everybody else so everybody has a consistent worldview if possible. And the last rule is maybe the greatest innovation that Bitcoin has introduced, is to make the block creation process really, really hard. Basically, computers that have to create a new block have to churn out a very, try to find answers to a very difficult cryptographic puzzle, one that it takes the entire network around 10 minutes to find for every time. So a block is created once every 10 minutes or so. And the reason this is made so difficult is because while it's very easy to join the network and do so under many false identities, an attacker might join and pretend to have 1,000 nodes on the network, it's very hard to obtain a large portion of the computational power. So if you want to do these, the block creations or to vote on the history of events, you have to do a lot of computing, and this is something that helps protect the currency from attack. So these 3 rules together give us Bitcoin's security, and I'll show in a second what might happen if an attacker tries to take advantage of the system. Right, so let's assume we have some transaction. I'm maybe the blue guy. I'm a merchant who received payment for some services, and I want to make sure that the money will remain in my hands, somehow that this transaction will not vanish or be reversed. An attacker might take advantage of Bitcoin's rules, the longest chain rules specifically, and might try to reverse this transaction. So, for example, if he shows us another fork of the blockchain containing a conflicting transaction that reroutes this money to a different destination, everybody is supposed to take the longest chain as the real truth of the real sequence of events, and the money that I thought I was holding in my hands suddenly vanishes. So this is known as the double spending attack or the double spending problem. And this is how it manifests inside Bitcoin. It also shows up in other systems pretty much everywhere where money is being moved. So why is this difficult? So the hint is in the fact that the attacker has to show us a very long chain of blocks, right? And every creation of a block is very hard computationally. You have to do a lot of computational work to do so. While the attacker is solving these computational puzzles needed to create these blocks, the network is still building this chain. So it's racing with the network to try to outcompete it, right? Try to outbuild blocks faster than the network can churn it out. And here is where Satoshi's great idea actually works. We have a theorem from his original paper in 2008 that basically guarantees that we'll be safe. So if the attacker controls less than half of the compute power in the network, and nodes can send blocks quickly to one another, those are the two main conditions, then we can really be safe after our transaction is embedded in deep enough in the chain. If we see a transaction and many blocks have been built on top of it, we know that the probability for replacing a block goes down exponentially fast. So you could be assured after maybe just 6, 7, 8 blocks that the probability goes down quite quickly. Unfortunately, what this means for Bitcoin is that given that blocks are created only once per 10 minutes, you have to wait quite a while until you're fairly certain that money cannot be reversed. But still, this is orders of magnitude faster than if you think about compared to maybe bank transfers, right? If you're sending money via a wire transfer, it could take several days to get to the destination. So in this case, Bitcoin outperforms other currencies. And you might also take a risk and say, OK, let's assume my transaction just appeared in one block. I don't have to wait for it to be very deep. And still, I'll consider it sufficiently accepted. And this is what actually merchants do today. So this was my overview of the protocol. Now I really want to start and try to show where other innovation in computer science hits. But maybe a word first about how the protocol gets upgraded. One of the problems when you have a protocol that has to have everybody agree on information is that when you need to make an update to the protocol, you have to deploy it everywhere at once. If something is not backward compatible and somebody does not agree with the information of others, you're at risk of basically splitting the system. This guy is not in consensus with others, and he's not contributing to the blockchain. So several updates to the protocol have already been done, but some of them are not backward compatible. One of the recent upgrades is called SegWit. This is actually one that's been inside the code. It's been deployed to Bitcoin's code base, but it's waiting for 95% adoption. Basically, when 95% of all the blocks are created, have announced that they will support SegWit, this feature will turn itself on in all of the machines around the network, trying to synchronize this together. So this is, in some sense, very conservative behavior on the side of the people developing Bitcoin. This is because they are really worried about breaking this very large, very complicated machine that's worth, that's holding a lot of money. So they are prone to do more incremental changes, and in some sense, this 95% rule shows that they prefer stagnation to controversy. So some features that have been desired by some are not accepted by everyone. They therefore do not get accepted. If there's no consensus on the protocol itself, there can be no consensus on the data. So a lot of the innovation in blockchains and cryptocurrencies is actually moving to what's called altcoins. These are alternatives to Bitcoin that took the source code and replicated it and are doing experimentation on top of that. So you get to see a lot of the nice, innovative stuff and a lot of the crazy stuff as well in these altcoins. And they are, in some sense, the proving grounds for new advances. So one of the limitations that's been bothering people the most is that Nakamoto's consensus protocol, as it's embedded in Bitcoin, is not very scalable. So you might be worried about the fact that every node on the network has to hold the entire blockchain with the entire history of all transactions anywhere in the world. That's very restrictive. But that's not the biggest problem of them all. If you really do the math, every transaction is fairly small. That's not a really big problem to support such high volume of trade. The real problem in Bitcoin comes when you start to think about what happens when you increase the number of transactions and what it does to the blockchain. So if you want to have more transactions per second in Bitcoin, you basically have two options. One option is to use larger blocks. Bitcoin blocks today are 1 megabyte, which holds around 2,000 transactions. You might try to scale them up to 2 megabytes, 3 megabytes, 100 megabytes maybe. Or you might start to create more blocks per second. Maybe instead of 1 block every 10 minutes, maybe you'd want to have 1 block per second. Maybe we wouldn't have to wait as long for money to go through the pipes. So the problem that this leads to is that the blockchain itself becomes more forked. It has more forks in it as blocks are created almost at the same time in the network because larger blocks take longer to propagate to other nodes. While you're sending your block, your 100 megabyte block to someone else, he may already have found another block on his own by solving this computational puzzle, which does not build upon your own, and so they are competing in the chain. The result of this is that the blocks that are added do not necessarily increase the size of the chain. This is basically wasted effort that gets thrown away. We have a lot of consequences to this, and maybe the most severe one is that the security of the currency is compromised. An attacker can show up with a longer chain, and he doesn't have to create as many blocks as before, right? Because all of these blocks that were created by honest nodes did not contribute to the length of the chain. It's much easier to overcome. So there's a lot of work that's been done on alternative protocols and improvements to Satoshi Nakamoto's consensus protocol, and I have my own paper with students on this. So we've proposed something called the Specter Protocol. Specter takes this idea of voting on the blockchain as blocks and basically generalizes the blockchain structure. Instead of using a chain where blocks would just point to a single predecessor, they might now point to more than one, right? Any block that you heard of, you are supposed to reference somehow, either directly or indirectly. And I won't go into the details, but this sort of structure gives us the power to do consensus much faster. So Specter can scale to several blocks per second. We've done simulations with 10 blocks per second. And it can give you a guarantee that money does not get reversed after several seconds, which is good enough if you're at the cash register, right? You're paying for your groceries with Bitcoin or whatever cryptocurrency it is, and you want the payment to come through. So there are other proposals that people are working on repeatedly. So I think this is an area where we're going to see dramatic improvements. Another very important aspect of Bitcoin is privacy. The blockchain is replicated everywhere at all nodes on the network, which basically means that whenever you're moving money around, everybody gets to see every transaction, right? So Bitcoin maintains some level of anonymity, or more precisely pseudonymity. You can transact in Bitcoin under these pseudonyms. Basically, your account number or Bitcoin address is just some string of characters that nobody can really easily tie to your identity in the real world. But still, if you follow these changes over time and you record them, you can see a lot of information going on the blockchain. So this graph that you're seeing here is actually a trace of money that I did manually. We had a student at the Hebrew University who came to me and said that his mother's computer was hacked, and that the person who hacked the computer encrypted all the files, and he was now getting requests for ransom that was to be paid in Bitcoins. So I asked him if he was going to pay the ransom and if he could give me the address to follow it. So he was actually infected by a specific form of malware called Loki. And what you're seeing here is the operator of lock key pulling together many, many ransom payments together. One of these is our students' ransom payment. And these were pulled out into chunks of 50 bitcoins and brought together with other ransom payments of a similar type. And eventually they are sent to what we definitely know is an exchange in Russia. Basically, this guy is cashing out his ransom payments for euros or dollars or something of this sort. So this is just a small snippet, but actually once you start digging into this data, you can see maybe a month's worth of Loki's ransom payments getting aggregated together, 100% of them going directly into that exchange in Russia into the same account. So this is just to show you that information is still getting out, and Bitcoin's use for criminals is notoriously because of its anonymity, but if you look at this criminal who's been ransoming people's data was not actually interested in Bitcoin's privacy. You can follow him very easily. I think the fact that money is laundered in Russia was more important to this guy, right? So you couldn't get to that exchange and have them reveal who their clients are. That's maybe where the laundering actually takes place. So to solve this problem of privacy, one of the most recent innovations in that area came from a very deep and very interesting work in theoretical computer science, which involves something known as zero-knowledge proofs, or non-interactive zero-knowledge proofs. So this is a little bit technical to explain what a zero-knowledge proof is, but I'm going to do my best using a physical analogy. What does it mean to prove something and have zero knowledge, in some sense? So suppose there's a store that allows you to buy some food for a fixed price as long as you don't take over 1 kilogram. Okay, and I want to buy some cookies at that store, but I don't want the person at the cashier to know what I bought. I don't want him to know that these are cookies. I don't want him to know the exact amount that I bought. I just want him to know that it's under 1 kilogram. So here's what I can do. I can take my cookies without him looking. I can put them in an opaque box. And I can walk up to the cash register, and I can place them on a scales, right, on these scales. And if the scales tip right against this weight of 1 kilogram, then we know that whatever's in the box weighs less than that, and we don't know what it is, right? So in some sense, I've proven something about the contents of the box. I've proven a property that they have less than 1 kilogram. We don't know what's in the box. We don't know how much. So there is zero knowledge about anything else than the thing that I just proved, right? That there is less than 1 kilogram of matter inside. So this is a physical analogy. The wonderful, wonderful thing about computer science is that you can get to do that with information. You can prove that you have information in a computational sense. It's a very, very deep area of computer science. And just until recently, this sort of thing was not applicable. You couldn't run software that did zero-knowledge proofs in reasonable time. But recent advances in the field have allowed you to do very simple computations in several seconds. So this was immediately applied to blockchains. And there's now a new cryptocurrency called Zero Cash that uses zero-knowledge proofs to gain privacy. And I'll try to explain this again by caricature, just to get the basic notion of what's happening. So suppose there's the blockchain right here, and Alice owns a coin. And she wants to say that on the blockchain, but without revealing this information. So instead of putting our cookies in the box, we're going to take our private information and put it in a virtual box of sorts. We're going to encrypt it, or rather hash it, and put it on the blockchain. Right? So Alice now did not reveal to the entire world that she owns a single coin because nobody can read beyond the encryption. It's an opaque box. Now, if Alice wants to send her money to Bob, what they would want to do is create the same box for Bob, saying Bob owns 1 coin, and put it on the blockchain, and eventually erase Alice's or invalidate it in some way. But the key problem here is that this information is encrypted, and we don't know that what Alice wrote inside of Bob's box is the same amount of money that she had. we want to know that when Alice sent Bob money, she didn't create any out of thin air. That this doesn't say 10 coins where Alice only had 1. So this is where zero-knowledge proofs come in. And basically, what you'd want to prove is that the amount inside of Bob's box here is equal to the amount that Alice had in her box before. So think of the scales as the analogy here and how you would do it in a physical world. And the real magic is how to do it in a computational setting. So this is just a taste of zero-knowledge proofs. Another issue that comes up very often in the context of blockchains is smart contracts and how we'd want to start doing more fancy things when we move around money. So you could consider a setting like a swap when you want to trade with somebody, let's say dollars for euros, and they're both living on this blockchain. You can send orders to the blockchain to move money. So two parties that agree to exchange maybe dollars to euros would first talk amongst themselves, and then one of them would say, okay, send the dollars to the red guy, and the red guy would send the euros to the blue guy. The problem is, of course, what happens when one of them fails to deliver and only the other has sent the money, right? And this happens very often in financial systems today where we have these broken promises that don't take place. Sometimes settlement doesn't happen as we wanted. So what you could do to try and solve it is, this a regular trick in computer science. You could try to do an atomic swap, just have both of these occur at the same time. And Bitcoin realized this fairly early, that you could do things with your messages. You can say things that could be interpreted as a contract in some sense. Let's say, for example, the blue guy says, I agree to send dollars, but only if I get euros in exchange. And the red guy says, I agree to send euros, but only if I get dollars in exchange. So when these two appear on the blockchain, everybody sees them. They know that there's agreement. No money has to actually move anymore because we can consider the funds as already being transferred. Right? The very existence of these messages on there is the transfer of money. So as you take this to the extreme, you can start thinking of fancier things to do with messages to the blockchain and to the computers that run it. And the extreme is maybe the Ethereum system. And Ethereum is another type of cryptocurrency that takes this as maybe thinks of what people send as inputs to computer programs that are running by all of these computers together. And they are actually checking each other's work. So instead of having just a log of transactions and transfers, what Ethereum would have is a log of the computation being performed. So this led to very interesting systems. One of these programs that was running over Ethereum was called the DAO. You may have heard about it on the news. The DAO is actually a program that coordinates investments. Everybody who paid into this computer program or contract basically got shares of the DAO. And that could then vote and say where the money that the DAO holds collectively would be invested. So you can think of it as a venture capital firm running by many people who just sent money to a computer program running on the blockchain. It's a little bit extreme. The surprising thing about the DAO is that it raised a lot of money, $168 million. This wasn't in actual dollars. It was in Ethereum's internal currency called Ether. And here you can see a snippet of code. This is the description of the DAO. It's a computer program, nothing more, nothing less. And it controls how money is handled and how votes are taken and all of the input that is collected from users. Maybe the second most surprising thing about the DAO is just I think weeks after it was launched, there was a bug in the code that was found in the exact snippet of code that I showed you. Basically, when you withdraw from the DAO, you could take away your earnings, at least the fraction of them that belongs to you according to the internal records. And this is the function that did it. So it would send you the money, and then it would zero out your balance. The problem is that the attacker could actually insert code that runs between the transfer and the balances. You could actually run something every time you get money. You could have a small program run, maybe place some of the money in savings accounts or something of the sort. Once the attacker understood that he can inject code in between the transfer and the zeroing of balances, he simply used that same code to call this function again. So he would have the transfer invokes his code, which calls the transfer again, never zeroing out his account balance. He could just repeatedly empty these accounts. So this is a very, very simple bug. It would have been fixed if these lines have been in reverse order. That's simple. Unfortunately, that cost the DAO theft of around $50 million. So that was very sensational. And Ethereum have actually decided to apply an update to the entire system to get the funds back, which was very controversial. You're not supposed to deal, to update the system every time somebody hacks into some specific account or someone's contract. Ethereum was built to guarantee everyone the execution of the code as it is without any regrets and any ability to change it back. So somebody ended up writing a letter to the Ethereum community posing as the attacker. It's probably not from the attacker. But he was basically saying, you know, I carefully examined the code of the DAO. It is not really hacking what I did. If you read the terms of the DAO, they say, the terms of the DAO creation are set forth in smart contract code existing on the Ethereum blockchain, right? If there's any disagreement about what the terms are, you should read the code. And he said, what I did was read the code better than others. And so what I did was legal, right? I just executed the code on Ethereum, right? So we're entering this world where law is actually code, a computer program. And your lawyer might actually be a hacker trying to look for loopholes in this code, in this contract, or an attorney trying to build, right, a programmer trying to build a contract without any loopholes. So what we need is good old-fashioned software verification. Here's where computer science again interjects on something, on legal matters. Another question you might ask yourself about Bitcoin is, are the incentives within the system aligned? Nodes in the system get paid with Bitcoins every time they create a block. They get fees. And they invest computational power. And a very nice series of works has shown that actually you could deviate from the protocol and do much better. You can earn more money. And there are already improvements to the protocol that we know of that can solve this problem partially, but this is still an area of active research. So incentivizing the protocol correctly would ensure that it runs well. Other aspects of Bitcoin are, for example, network level security. You can think of what happens when you don't allow nodes to send blocks to one another, maybe by attacking the network's infrastructure from beneath. This turns out to be kind of catastrophic for Bitcoin, and given the fact that the internet is very easy to manipulate and to attack, also means that we need to improve systems in that direction. So I'm running out of time, so I'll summarize. I hope I got you, I convinced you, I managed to do my job and to show you that there are many challenges in cryptocurrency systems. I just gave a few tastes in some selected areas. There are a lot of new developments coming out. Most of them show up and get tested in these very wild environments. There are many, many others that I did not mention, very exciting stuff I had to really pick. And that this is a really new CS application domain. So I'll thank you and stop here. Thank you.
Again, we have time for a couple of questions, and you can raise your hand over here. There's a microphone right there.
Thank you so much for the talk. So blockchain is a distributed ledger, and Ethereum and Bitcoin are two examples using it for cryptocurrency. Okay, so now there's a lot of other applications outside finance and cryptocurrency. So I just wanted to ask if you're familiar with Hyperledger, which is trying to build build a code base or if you like, for various applications, and how is it different, or just in general, if you can situate it in the taxonomy?
Okay. So the systems that I was discussing mostly are these public open systems where you don't know the identity of participants. They have their whole politics and so on, trying to build these systems that are open and give service to everyone. Hyperledger and other commercial enterprises have taken ideas from Bitcoin, the smart contracts, the consensus, and so on, and have brought it back to the setting that is a little bit easier, where we know who the participants are. We can do the consensus protocol a little bit better. It doesn't require solving these hard computational problems. There are other things that we save along the way, and maybe we can process transactions faster. Going back to what is already has been solved and very well researched in computer science, consensus protocols in classical settings. And the hope is that they would have a business impact, right, where you would remove a third party, like Bitcoin has done with banks in that sense. So Hyperledger and other initiatives, there are quite a few of them that are trying to build code bases for this, are all banking on that.
Let's take the question at the back.
Professor, I saw you had an excellent slide using a decision tree framework, which looks very similar to a slide I saw in the MIT Pressbook on machine learning for classification. There was a decision tree model for machine learning. Is that similar to the decision tree that you were showing a few slides ago?
No, so I think the trees that are here are not so much decision trees. I don't know how AI and other machine learning goes into blockchains and integrates with it. Probably this data as it's shared is going to be interesting to analyze, but I think machine learning is one of the areas that we haven't seen integrated into blockchains so much.
In the interest of time, I'd like us to thank Aviv